Okay, now we will continue from Node-RED, follow example. And let's start at the top with the Modbus reader. This node is polling a PLC on a fixed interval. The address starts at 0. We are reading 10 holding registers and the rate is 5 seconds. And why 5 seconds? Because on a shop floor, you usually don't need milliseconds updates for production metrics. Faster than just race, bandwidth, and CPU. Slower than that, and operators start feeling blind. This is a deliberate trade-off. So look at here. Now the data coming out of Modbus is just raw registers, integers with no context. And that's useless by itself. So this function node is where engineering judgment shows up. We extract production count, downtime, cycle time, whatever matters for the machine. Then we compute OEE. OEE is availability times performance times quality. Availability is based on downtime, performance is based on cycle time versus ideal, and quality comes from good parts over total parts. And the math is not shown line by line here, but the intent is clear. We are turning electrical sickness into business metrics. Okay, now once we have structure metrics, we write them to InfluxDB, and here notice that measurement name is machine metrics and precision is milliseconds. That's important. Time series databases live and die by time stamps. If you mess that up, every dashboard and analysis downstream becomes garbage. Retention policy is autogen, which means we are letting influx handle lifecycle rules separately instead of breaking them into the flow. Okay, and in parallel, the same payload is published to MQTT. Same data, different consumer. The topic factory slash line CNC001 tells you exactly where the signal belongs in the organization. And course is set to 1, which means at least once delivery. In industrial monitoring, missing a message is worse than receiving a duplicate. That choice reflects operational priorities. Now, look at the alert check. This is a simple threshold, OE less than 70. The 70 is not a random number. Below that, you are burning money. This switch node is effectively encoding a management rule into software. When the condition hits, the flow branches. Okay, and that branch ends with an email alert. Old school, maybe. Effective, absolutely. Maintenance teams still live in email, and the fastest way to get attention is to land directly in their inbox with a subject that states exactly which machine is underperforming. Okay. Now, let's shift gears and look at the backend code that talks to InfluxDB. Here. So, this Python class is doing the same job as Node-RED, but from an application perspective instead of flow-based one. So, here are libraries, and look at that. The constructor sets up the client, the write API, and query API. Okay, synchronous writes are used here, and why synchronous? Because in industrial logging, you often prefer certainty over raw throughput. If your write fails, you want to know immediately. Okay, and in write machine data, we construct a point called machine metrics. Tags like machine ID, line, and plant are indexed. Metadata. Fields like temperature, vibration, production count, and energy consumption are actual measurements. This distinction matters. Tags for filtering. Fields are format. Mixing them up kills performance later. Okay. and the timestamp is set using UTC now with nanosecond precision. And nanoseconds might sound excessive, but when you start correlating vibration spikes with process events, you will be glad you kept that resolution. Okay, now there is a separate method for quality data. Different measurements, different semantics. Dimension X, dimension Y, surface roughness, and path are quality attributes, not machine health sickness. And storing them separately keeps queries clean and intentional. And calculating parts here. Calculating OE from raw data. Now, here the Flux query pulls mission metrics, filters by mission ID, and selects only the fields we care about. And this is where time range equals 1 hour by default. 1 hour is a common operation window. Short enough to react, long enough to smooth noise. Okay, that's done. And what is next here? We have health trend analysis. Vibration and temperature over 7 days aggregated into 1 hour means this is classic predictive maintenance. We are not looking for one bad point. We are looking for drift and slow changes that humans miss but databases don't. That's done. And downsampling part or task. Raw data goes into an industrial raw bucket, then gets averaged hourly into industrial downsampled. And why do this? Because storing high frequency data forever is expensive and mostly pointless. Summaries are what you use for long-term analysis. And at the bottom you see example usage. We initialize the logger, write sample mission data, query trends, print them, and close the connection. That's a full loop. Ingest, store, analyze, and act. Okay, and Grafana here in the JSON. Let's start with this dashboard configuration. The title tells you the intent immediately. What's that? Manufacturing line OEE dashboard. This is not a generic dashboard. It's opinionated. It's focused on operational performance. The time zone is set to browser, which sounds trivial, but it matters. And operators in different plans see time aligned to where they are, not where the server lives. Okay, and here the first panel is a gauge showing real time. The query pulls from the industrial data bucket, logs back 5 minutes, and filters on the OE calculation measurement. 5 minutes is short on purpose, and this gauge answers a single question. How healthy is the line right now? The mean is 0, the max is 100 because OE is a percentage. The thresholds are set at 0, 70 and 85. Red below 70 means intervention territory. Yellow means watch closely. Green means the line is behaving as expected. This color logic is encoding tribal manufacturing knowledge directly into the UI. Okay. Sorry. Now, we switch visualization type entirely, and this one is a time series, same data source, longer window, 24 hours. The reason is simple. Production count only makes sense as a trend. A single number tells you nothing. The slope tells you everything. And flat lines mean stoppages. Sudden spikes might mean counter resets or data quality issues. And this panel helps you reason about behavior, not just state. Now notice the heat map for mission temperature, and this is subtle but powerful. Instead of staring at individual lines, you see density and intensity over 12 hours. Heat maps are excellent for spotting patterns that humans miss in line charts, like gradual thermal buildup during certain shifts. Then we move to energy consumption displayed as a bar gauge. This is where operations and sustainability start intersecting. Looking at the last hour forces near real-time accountability. All machine consuming disproportionately more energy is either doing more work or wasting power. And this panel helps you ask the right follow-up question. And quality metrics are shown as a stat panel aggregated over 24 hours. The alias says pass rate percent. That wording matters. Operators don't want raw counts, they want ratios that reflect outcomes. One number, clearly labeled, reduces cognitive load. Okay, and code part is down for now. Here you see complementary platforms that often show up in real deployments. Kafka is about scale if you need to move millions of events per second across multiple plants. This is where you land. Prometheus focuses on system health rather than process metrics. TimescaleDB appeals to teams that live comfortably in SQL and want a time series without learning a new querying language. So Ignition SCADA is here, sits closer to operators, combining HMI, learning, and control room workflows. Each tool exists because it solves a specific class of problems better than the others. Okay, we can continue, right? Yes. Now, look at that architecture diagram. Align, okay. Now, this follows the Purdue model, as also known as ISA 95. Look at that. At level 0, you have sensors and actuators. So, these are physical devices producing raw signals. Level 1 is the control layer with PLCs, deterministics, real-time, safety critical. You don't mess with this layer casually. Level 2 is where our IIoT gateways live. This is the bridge. Protocol translation, HNTX, local buffering, security controls, container orchestration. And this layer absorbs complexity, so higher layers don't need to understand field protocols. And notice the security and DM as the block of to the side. Industrial firewall, VPN gateway, intrusion detection, certificate authority. This is intentional isolation. Okay. And you never expose control systems directly to enterprise or cloud networks. Segmentation is not optional, it's survival. And level 3 includes MES, SCADA, and historians. This is where production context, operator interaction, and long-term storage happen. Level 4 is enterprise and cloud. Here, ERP systems, cloud IoT platforms, business intelligence, and this is where executors live, far remote from sensors but still dependent on their data. And execution or roadmap. Okay, now phase 1 is assessment. You inventory assets, identify protocols, define KPIs, and calculate ROE. Skipping this step guarantees failure. And phase 2 is design. Network architecture, hardware, software stack, security. Decisions here are hard to undo later. Okay. So Phase 3 is the pilot, one production line, validate connectivity, test analytics, break things safely. Phase 4 is scale, rollout across the facility, standardized configurations, and train operators. This is where operational discipline matters more than clever code. And optimization or continuous improvement at machine learning models, expand use cases. The system is never finished. It evolves as the business evolves. Okay. Another important thing. We will going to zoom all the way down into the engine room of the gateway and explain why this Docker Compose stack looks the way it does. Because every service here exists to solve a specific industrial constraint. And the first thing to notice is that everything is containerized and tied together with a single compose file. That is not about convenience, that is about repeatability. If a gateway fails on the factory floor, you want to redeploy the exact same software stack on new hardware without surprises. Okay, and we start with the MQTT broker. Mosquito sits at the center because MQTT is the lingua franca of IIoT. It decouples producers from consumers, and PLC adapters, analytics engines, and dashboards don't need to know about each other. They just publish and subscribe. Exposing port 1883 supports standard MQTT, while 9000 is there for WebSocket access, which is useful for browser-based tools and diagnostics. And the persistent volumes matters because losing retained message during a restart can break downstream logic. Okay. And next is the time series database. Here, InfluxDB is initialized in setup mode, so the system bootstraps itself without manual clicks. The organization, bucket, retention periods, and credentials are defined as environmental variables. That means configuration lives alongside code, not in tribal knowledge. And the 30-day retention is a deliberate edge decision. You keep enough data locally for troubleshooting and short-term analytics, while long-term storage belongs upstream in historians or the cloud. Now, here, Grafana comes next. And notice a dependency on InfluxDB. This ensures the visualization layer never starts before the data layer is available. And provisioning volume is critical. Dashboards and data sources are treated as code. So if this gateful is rebuilt, the dashboards come back automatically. That's how we avoid handcrafted dashboards drifting over time. And Node-RED plays the role of glue logic. This is where low-code flow-based processing shines. Serial ports are passed directly into the container, which tells you this gateway talks to real hardware, not simulations. And mapping the time zone explicitly prevents subtle timestamps bugs that only show up during daylight saving changes. Okay, and Telegraph is responsible for ingestion. It collects metrics from devices, containers, and protocols and pushes them into InfluxDB. And mounting the Docker sockets allows it to observe container health, which is essential for self-monitoring. If the gateway is sick, you want to know before production is affected. Okay, and this service is the protocol translator. Modbus is chatty, synchronous, and not cloud friendly. MQTT is lightweight and asynchronous. By mapping Modbus registers to MQTT topics at the edge, you isolate legacy constraints. And you know, the baud rate, serial device, and broker address are parameters, not code changes. That's how we adapt to different machines without rewriting software. And the OPC UA gateway handles a different class of equipment. Instead of serial registers, you are dealing with structured address spaces and security contexts. The server URL is explicit and publishing into the same MQTT backbone keeps the rest of the system unaware of protocol differences. And this is architectural insulation in practice. Now, then comes the analytics engine. This is where raw signals become insights. It connects directly to InfluxDB using tokens, not passwords, and reads from industrial data bucket. Models are mounted as volumes, so you can update analytics logic independently of the runtime. That separation is what makes continuous improvement possible. Okay, and here Portainer is included not for production users, but for operators and engineers. It provides controlled visibility into running containers. On a remote site, this can be the difference between resolving an issue in minutes versus hours. Okay, and here, what can I say else? I think that's okay for this lesson, and we will continue from there.